And hello, welcome back. Looks like the mic's on good. Yeah, welcome back to this video on OpenFOAM, or rather the OpenFOAM Intermediate series. Last video we were talking about some LES simulations, how to set it up in OpenFOAM. Okay, and what we realized, okay, I mean, you realize it's pretty simple to do stuff like that, all right? It's not that difficult to do a RANS or LES simulation, but it's more difficult to make sure it's accurate and stable. Okay, so a few videos ago, just want to continue where I left off. A few videos ago, I actually tried to run a Spotlight Armorer simulation, and we were getting some problems. Okay, I was getting some problems where the time step was moving smaller and smaller. And if you take a look at the Courant number, I assume you know what the Courant number is. Yeah, so if you're not sure, you can go check out some other videos. But this, I assume you know it in this video to have made it this far into OpenFOAM. Okay, but okay, in case you forget, okay, I'll just do a very quick one for you. Okay, so let's say you have a cell, a square cell like that, and you have some velocity, all right, u, okay, and your time step is delta t, and this cell width is a cube and is delta x. The Courant number is actually, or the Courant-Floyd CFL number. There are three famous engineer scientists who came up with this number, or at least their names are associated with this number. This is actually u delta t over delta x. All right. What it means is that, okay, if your velocity and time step, this length scale is longer than the cell width, tendency is for the simulation to become unstable. Or else, the other way of thinking about it is that a fluid particle can flow from here and completely miss the cell after one time step. So this is T1, this is T2. So a fluid from, let's say, the adjacent cell can actually totally skip this cell in the next time step. Now there's nothing inherently wrong with that, but it's unstable, and it's unstable, but you can solve it by doing a little bit of tweaking to the Pimple algorithm. And I kind of mentioned that before, by setting the outer correctors to be very high and setting your relaxation factors to the right value, you should be able to make this simulation stable. Unfortunately, you will not be able to capture small velocity fluctuations on length scale smaller than u delta t. You cannot capture those very small fluctuations at all. Okay, so this is basically what Courant number is about. So yeah, you can see that the mean Courant number is very, very small. Means the velocity times time is a very, very small fraction of the total, this delta x. This is what the mean Courant number is showing. However, you can see that the maximum Courant number is actually 0.517. That means the velocity times time is about half. Now you have that going on. Hold on, let me check the time remaining. I have 15 minutes. Okay, 15 or 16 minutes. Okay, so let's say we think about it this way, right? So the mean Courant number is actually minute, terribly small, but the maximum Courant number is like 1,000,000 times bigger, or a few 100,000 times bigger. So what happens? It's basically saying that in one of these cells, the velocity, this Courant number, the velocity, okay, because time step and delta x is constant, one of these cells has a velocity so big compared to the rest of the surrounding cells, that you have this gigantic Courant number. And not only that, with every time step, this velocity is getting bigger. So you see, OpenFOAM tries to keep this Courant number at 0.5, the maximum Courant number at 0.5. But I see your delta t is actually 1.55 times 10 to the minus 15. That is minute. That is very, very small. And what's more, OpenFOAM is trying to reduce this time step even further, to reduce the Courant number to about 1 times 10, to about 0.5. But you see, with a huge kind of a significant reduction in Courant number, the maximum Courant number only, hold on. Yeah, the maximum Courant number is just increasing and increasing and increasing. So, okay. Well, it's not exactly increasing here. You can see that the Courant number is roughly the same, even with a decreasing time step. Okay? So, alright. Maybe just now I wasn't explaining too clearly. The time step wasn't constant. Okay? I mean, the time step is not constant from going from one iteration to the next. However, within one iteration, the time step is constant, and that's the comparison I was making between the maximum and the mean Courant number. Now, if the time step is decreasing, but your Courant number stays the same, and this delta x stays the same, what is increasing? So obviously the velocity is increasing. So why is this velocity in one of these cells increasing? I'm not completely sure, but you could classify this as a form of instability. Okay, you classify this as a form of instability where there is probably some numerical instability there. I don't know what kind of numerical instability it is, but it is a numerical instability, and that results when you have one small error, and the error is growing bigger and bigger and bigger, such that the whole simulation starts to become unstable, as probably what you are seeing over here. The simulations become very, very, very unstable. Okay, so that's the idea over here. Okay, how do we then dampen out these instabilities? How do we try and cancel them out? There are a few ways. One is by using a coarser mesh. Okay, you can use a coarser mesh, or you can use a more structured mesh, because usually I think sometimes the reason why some of these simulations are very unstable is because you have a very poorly structured mesh. Okay, so I'll go to this Spalot Almaras. You should be able to see. Okay, and if we take a look at the surface with edges, alright, and let's insert a slice plot. Okay, with this normal, and I'll use surface with edges, then you can see what the mesh is like. Alright. Alright, so you can see that the mesh at the sides are very very weirdly shaped, as you can see here. I'm using my left and right mouse to pan. Left and right mouse buttons to hold, click and pan, and then the right mouse button to zoom in and out. So you can see that the meshes here are very, very weirdly shaped sometimes. The rest are okay. It's just probably those at the corners that are a little bit more problematic. Okay. Alright, so again over here you have some very strangely shaped mesh. Okay, so that's what it's about here. And you can see over here the mesh is kind of very weirdly shaped. Okay, you have small meshes like these, and these can actually cause some instabilities. So what is my preferred way of dealing with this? If you have a Reynolds average Navier RANS type simulation, Reynolds average Navier-Stokes, and you don't need to resolve very small fluctuations, such as you're trying to resolve an eddy. Okay, if you're not trying to resolve eddies as normally you would in a LES or a direct numerical simulation, if you're doing a Reynolds average Navier-Stokes, it is okay to let your Courant number exceed 1. So sometimes what I like to do, I don't know whether it may work, I would increase the Courant number to be more than 1, so that you can go and change in system control dictionary. So in fact, I have the maximum Courant number here to be 100. I can do that. And then how do I make it stable? Go to fvSolution, and again we try our tricks with the relaxation factor. So I put 0.5 for example. Okay, so I'll give a relaxation factor of 0.5. Okay, and that should about do it. Hopefully you'll get it done, within convergence. And then the pimple algorithm, I'll need to increase the number of outer correctors, which is over here, and outer correctors I need to increase it to some very high value. So for example, maybe 1000. Okay, so I'll just leave it as such. And let's see, check mesh to see whether I have any meshes available. So there is a mesh there. I can just start running pimple foam straight away. Okay, so that's one of the ways I deal with this kind of issue. Okay, so it will start to run, as you can see here. Okay, so it's going to run a few rounds of this pimple iteration. You can see in the initial when they start guessing these pimple iterations, you have this initial residual of 1. What does it mean? It means that the final solution and the initial solution, alright, let's think about it this way. So they're trying to solve for a matrix, right? They're trying to solve for a very big matrix. But the idea is that you have the initial guess, and the final solution. Okay, between the initial guess and the final solution, there will be some difference. Okay, some different, I don't know what's some delta. Okay, some delta. Okay, so if you have this difference between the initial and the final solution, okay, how do you say? Well, okay, I won't call it the final solution. Maybe I'll say guess 1 or guess 2. Okay, so if you have guess 2, so this is guess 2 minus initial guess over guess 2. So that will be equal to residual. Now, if your residuals are very small, if you have a very small residual, you can more or less say that the errors between the initial guess and the next guess straight after that is small. You can more or less say you have reached a solution. So your initial residual is 1, which is fine. Your final residual is very small, but you can see once once we do one round of iteration of pimple, that means we solve for the velocities, and then we solved for the pressure equation. So the pressure equation is kind of the mass balance equation. The momentum equations are here. So you solve one round, and then because you under relax, you don't you don't go straight from the initial guess to guess 2. You go sort of take an in between somewhere here. So so how do we put this? Wow. Alright, so let's say you have a initial guess. Alright, and this is guess 2. Alright, so if you have a relaxation factor of 0.5, for example, okay, so initially you have this initial guess and then you have this guess 2. Once you finish this iteration, PimpoFoam will look at the relaxation factor of 0.5, and then it says the final guess 2. Okay, final guess 2. Okay, final guess 2 will be equals to 0.5 times the initial guess alright, or maybe I'll just put it this way so it's more clear. 1 minus 0.5 times of the initial guess plus 0.5 times of guess 2. Alright, so that's how basically the final guess 2 is worked, and this final guess 2 will become the initial guess of the next stage. Alright, okay, initial guess of this second Pimpo algorithm. So this will be maybe guess 3. Alright, so again, after some iterations, you'll figure out your residuals, and you can see the initial residual, how far this final guess 2, so to speak, is different from the third guess. Okay, that is actually equals to 0.2. Okay, it's about 0.2. So you see the initial residuals should actually decrease over time. So you see the initial residual initially was 1, then it becomes 0.202, and then 0.8, then it decreases some more, 0.09, 0.7, and ideally it should keep decreasing. So when it keeps decreasing, the idea is that you'll reach some point where it kind of stabilizes. So you can see it's not always going to stabilize. You see when it decreases, then it drops, then sometimes it increases, but overall the trend is that this residual here should decrease. Okay, overall the trend is that it should decrease. So you see it decreasing here over here, and it will keep decreasing, and the trend is good. It does keep decreasing, and finally the whole thing converges. That's how, you know, ideally you should see a solver converging. If you see these initial residuals grow and grow and grow, then we sort of have a problem. So let's see the other ones, whether they do converge. Okay, again the initial residuals are small, so they do converge there. It's very nice, and so far it looks to be okay. Okay, and when was the time that we actually got some unstable, something unstable? The time was actually about 0.08 seconds. So we'll let it run a while, and then hopefully we'll get some results later on. Okay. Yeah, so anyway, I think it'll take a while, so I'll probably come back to visit this matter in another video. Hopefully this Speller Omeros will work. This case will work, thus proving the point that making your Courant number big, it does help you average out all these numerical errors over time. So you don't resolve them, and this is good for Reynolds average Navier-Stokes kind of simulation. Yeah, and that should give you more or less an average of what's actually going on, and hopefully that actually helps you know how to do stability properly for this, in case you ever run into problems like that. But anyway, I shall not continue on too much. I shall see you guys next time. Thanks for watching. See you again.